The hook needs to be punchy, crisp air bites your cheeks. Snow crunches under boots. Above, the sky bleeds crimson streaks. A woman freezes mid-step, breath puffing white. The aurora isn't just light, it's a collision. Charged particles ripped from the sun's surface, hurtling through space. They pierce Earth's magnetic shield. Now they slam into the thin air above her. Oxygen glows green. Nitrogen flares violet. This isn't magic, it's physics. A century earlier, scientists wrestled with the same sky. In 1850, a British physicist, James Clerk Maxwell, studied magnetic storms. He saw patterns. Auroras danced where Earth's magnetic field was weakest. He proposed a connection to solar activity, but the proof eluded him. The sun was too far, too distant. How could it stir the polar skies? The key came in Norway. In 1896, Christian Birkeland built a vacuum chamber. Inside, a magnetized ball represented Earth. He shot electrons at it. They spiraled toward the poles. On the sphere's surface, light bloomed, the same light seen in the northern sky. Birkeland had recreated the aurora. He proved charged particles, guided by magnetic fields, struck the atmosphere. The sun was the source. Today we know the full dance. Solar wind, a constant stream from the sun, carries these particles. Coronal mass ejections send surges. Earth's magnetic field funnels them toward the poles. They collide with atmospheric gases. Oxygen emits green, the most common color. Nitrogen creates blue and purple. Strong solar storms push the lights lower. You might see them over Florida. The same process lights Jupiter's poles. But Earth's field also shields life. Without it, solar radiation would strip our atmosphere. Tonight, the same solar wind dances above you. The lights are a cosmic handshake, from the sun to Earth to the sky. You stand in snow, the sky bleeds green, a curtain rises, thin and sharp, then ripples like liquid light. Below, your breath hangs in the cold air. The green is everywhere, pulsing, shifting, a silent storm in the upper dark. This is not magic. It is physics, written in gas and light. Electrons slam into oxygen atoms in the upper atmosphere. The atoms vibrate, then release that green light. Nitrogen atoms hit harder, glow blue and purple at lower altitudes. The collision is violent. The atmosphere absorbs the energy, transforms it into color. One leading theory confirms this. The particles must carry enough energy to excite these specific gases. Earth's magnetic field steers them. It bends the solar wind like a river around a rock. The particles spiral inward, guided toward the poles. This creates the oval ring of light, the auroral oval, centered on the magnetic pole, not the geographic one. The oval shifts with solar wind pressure. Stronger pressure pushes it southward, closer to you. A coronal mass ejection can shatter the oval. It sends a surge of particles racing toward Earth. The lights surge south, visible over places like Florida or Spain. The same solar storm that bathes the Arctic in fire might paint the sky above a city you've never seen at night. The physics is identical, just intensified. Jupiter's poles burn with auroras. Saturn has them too. The gas giants have stronger magnetic fields and different atmospheres, so their auroras glow brighter, sometimes in ultraviolet. But the mechanism is the same: charged particles funneled by magnetic fields, colliding with atmospheric gases. The same cosmic process illuminates planets across the solar system. Earth's field does more than shape light, it shields life. Without this magnetic barrier, solar radiation would strip away our atmosphere molecule by molecule. The aurora is a visible consequence of that shield, light dancing at the edge of protection. Tonight, as you watch, the same particles stream from the sun, guided by Earth's field, colliding with air you breathe. The shield holds, the light endures. Cold air bites as you stand on frozen tundra. Above, the sky shivers. Green curtains ripple, then split into blue-violet threads. A sudden pulse, brighter, faster, like gas escaping a wound. You feel it, the vast, silent collision of solar wind against Earth's invisible shield. This is not mere light. It's a violent handshake between the sun and our world. Early theories missed the key. Why only at the poles? Why not everywhere? They assumed solar wind hit randomly, but sensors on satellites detect a funnel. Charged particles spiral along magnetic field lines, accelerating toward the poles like water down a drain. The field isn't passive, it steers the storm. Without this funnel, auroras wouldn't cluster in bands 67 degrees north and south. They'd be chaotic, global. Instead, they're confined, precise. Color tells the deeper story. Green often appears as oxygen atoms are excited by electrons in the upper atmosphere. Red appears higher, rarer from slower collisions. Blue and purple, nitrogen molecules struck harder. This isn't random. It's the signature of specific atomic interactions. If the sun sent just wind, no colors would map so cleanly to gas layers. The spectrum proves the collision physics is exact, particle energy matching atmospheric targets. Earth's shield holds, but it's a dynamic boundary. Strong solar storms push the auroral oval toward the equator, visible in cities like New York or Madrid. Satellites measure how deep the magnetic field bends. The stronger the storm, the more the field compresses. Yet the exact threshold, when a flare becomes a global display, remains elusive. We track particles, but not every flare's path. The next major event will settle it. What will the next solar storm reveal?